Welcome back to G Fun Facts Online, where today we are abandoning the theoretical for the tangible, diving deep into a technological breakthrough that is currently sitting in the vegetable aisle of your local grocery store. We are going to talk about slime. Specifically, we are going to talk about the sticky, viscous goo found inside okra pods, and how this substance, which chefs have used to thicken gumbo for centuries, has recently been weaponized by environmental engineers to fight one of the most pervasive threats to our biosphere, which is microplastics. If you have been following the news in the last few years, you know that the microplastic crisis has moved beyond just being an ocean problem. We have found these microscopic polymer fragments in the deepest trenches of the Mariana, in the pristine snows of Antarctica, and perhaps most disturbingly, in the placentas of unborn infants. The statistics are frankly terrifying, with recent estimates suggesting the average human ingests approximately 5 grams of plastic every single week. That is the equivalent of eating a credit card weekly through our water, our food, and the air we breathe. These particles act as rafts for dangerous pathogens and absorb toxic, persistent organic pollutants, effectively delivering a concentrated dose of poison to whatever organism swallows them. For decades, the municipal wastewater treatment industry has relied on a specific method to try and clean our water, a process called flocculation. To remove suspended particles, treatment plants add synthetic chemicals, most commonly polyacrylamide or PAM. These chemicals act like glue, binding small particles together into larger clumps called flocks, which then sink and can be filtered out. While this works for dirt and mud, it has a massive dark side. Polyacrylamide, under certain conditions, can break down into acrylamide, which is a potent neurotoxin and a probable human carcinogen. Furthermore, these synthetic flocculants are designed for organic matter, not plastic. They often struggle to bind with the smooth, hydrophobic surfaces of polyethylene or polystyrene fragments. So we are essentially using a synthetic polymer to try and clean up other synthetic polymers, creating a cycle of chemical dependency that creates toxic sludge as a byproduct. This is where the revolution happens. This is where the okra comes in. Recent breakthroughs in bioengineering have demonstrated that the mucilage, that slime found in okra and fenugreek, is not just a culinary quirk, but a highly sophisticated molecular net. This is not a home remedy. This is what is being called mucilage trap technology. To understand why this works, we have to look at the chemistry. Okra mucilage is rich in complex carbohydrates called polysaccharides, specifically pectin and galactomannans. Imagine these polysaccharides as long, tangled molecular chains. In their natural state within the plant, they store water. But when introduced to contaminated water, they perform a feat of physics known as bridging flocculation. When okra powder is dissolved in water, those long polysaccharide chains uncoil, forming a microscopic web. Most microplastics carry a negative surface charge, which causes them to repel each other and stay suspended in water, refusing to settle. Okra polysaccharides have specific functional groups, like hydroxyl and carboxyl groups, that interact with these charges. The long chains of the okra molecule physically hook onto multiple microplastic particles at once. Like a spider web catching flies, the mucilage pulls these isolated particles together. As more microplastics get tangled in the okra web, the cluster becomes heavy. Gravity takes over, and the entire mass sinks to the bottom of the tank, leaving clear water above. But the research gets even more granular. While okra is the star, it works best with a partner. Researchers at Tarleton State University, led by Dr. Rajani Srinivasan, discovered that fenugreek adds a crucial boost. Fenugreek seeds contain a different type of galactomannan structure that is chemically distinct from okra's pectin-heavy slime. Through rigorous testing, they found that okra is excellent at bridging larger gaps and working in salty environments, making it ideal for ocean water purification. Fenugreek, on the other hand, forms a tighter, denser gel that is incredibly effective in groundwater systems. When combined, they create a hybrid trap. The okra provides the long-reach arms to grab distant particles, while the fenugreek acts as the glue that holds the clump together, preventing it from breaking apart during filtration. The numbers backing this up are impressive. In controlled laboratory settings published in ACS Omega, the results showed that in ocean water, okra extract alone removed 80% of microplastics. Its molecular structure remains stable even in high salinity environments where synthetic chemicals often fail. In groundwater, fenugreek extract took the lead, removing nearly 90% of contaminants. And for freshwater, the researchers found a Goldilocks solution, a 1-to-1 blend of okra and fenugreek, which achieved removal rates of between 77 and 93%, depending on the specific plastic types. Crucially, speed is a factor. In water treatment, time is money. The okra fenugreek blend reached maximum efficiency in just 30 minutes. To achieve similar results, synthetic polyacrylamide often requires higher dosages and leaves behind non-biodegradable sludge. And this brings us to the most critical metric, which is safety. Even if a small amount of okra extract remains in the treated water, it is harmless. It is food. Conversely, residual acrylamide from synthetic treatment is a regulated health hazard. Now, you cannot simply throw whole okra pods into a wastewater tank and expect results. The engineering required to turn a vegetable into a reliable industrial product is sophisticated. Early experiments involved simple water soaking or maceration, but this is too slow for industry. Modern engineering utilizes microwave-assisted extraction. In this process, okra pods are subjected to controlled microwave radiation. This bursts the cell walls instantly, releasing the mucilage without degrading the polymer chains. This method increases the yield of active polysaccharides by nearly 50% compared to traditional soaking and reduces extraction time from hours to minutes. Bioengineers are also tuning these polysaccharides. By using enzymes or mild chemical treatments, they can graft new functional groups onto the okra backbone. For example, cationization involves adding positive charges to the naturally neutral or negative okra polymer, increasing its magnetic-like attraction to negatively charged microplastics. They're also exploring cross-linking, creating 3D networks of okra polymers that act like a molecular sieve, trapping particles physically as well as chemically. Once extracted, the slime needs to be stored. You cannot have rotting vegetables at a water treatment plant. Engineers use lyophilization or freeze-drying to convert the mucilage into a fine, shelf-stable powder. This allows plants to store sacks of white okra flock powder that can be kept for years and rehydrated on demand. Of course, the biggest hurdle for any green technology is economics. Can okra really compete with mass-produced synthetic chemicals? On the surface, synthetic PAM is cheap, costing roughly $1.50 to $3 per kilogram. Food-grade okra powder is currently more expensive, ranging from $10 to $20 per kilogram. However, techno-economic assessments conducted in 2024 and 2025 reveal that when you look at the total cost of operation, the math changes. The biggest saving comes from sludge disposal. Sludge containing synthetic chemicals is toxic, hazardous waste, which is incredibly expensive to dispose of. Sludge containing okra is compostable. It can be turned into fertilizer or biogas, saving plants millions in disposal fees. Furthermore, because okra flocks are often larger and settle faster, plants can increase their throughput, treating more gallons per hour. As governments tighten restrictions on acrylamide in water, the cost of using synthetics is rising due to compliance fines and monitoring requirements, making the green option the smarter financial choice. We are already seeing this move from the lab to the real world. As of 2025, several pilot programs are underway in agricultural regions like Texas, India, and parts of West Africa. These circular economy models take ugly okra, rejected by supermarkets, process it into flocculant, and use it to treat local irrigation water. But the potential goes beyond the industrial plant. One of the most fascinating aspects of mucilage trap technology is its accessibility. Unlike reverse osmosis membranes or UV radiation systems, this is low-tech hardware driven by high-tech knowledge. For disaster relief, in a hurricane or flood zone where water is turbid and contaminated, a packet of freeze-dried okra and fenugreek powder could act as an emergency clarifier, settling out mud and plastics before the water is boiled or chlorinated. There is also a growing movement of homesteaders and eco-preppers using okra slime to filter rainwater, reducing their reliance on microplastic-laden municipal supplies. Looking forward, we are entering the okra era. Agricultural scientists are now looking at breeding variants of okra not for taste, but for slime content. These industrial okra varieties would be inedible, woody, and packed with hyper-potent polysaccharides designed specifically for filtration. Material scientists are creating hybrid materials like okra graphene or okra chitosan aerogels, which are spongy, lightweight materials that can float on the surface of the ocean, passively absorbing microplastics without harming marine life. There's even speculative research investigating if modified okra polysaccharides could be used in dialysis machines to filter microplastics out of human blood, which would be a true medical frontier. The irony here is palpable. For years, we wrapped our vegetables in plastic. Now we are using vegetables to unwrap our water from plastic. This technology represents a fundamental shift in how we approach environmental engineering. It moves us away from the 20th century mindset of fighting chemicals with stronger chemicals and toward a 21st century biomimicry approach. By engineering the humble okra extract, we have found a solution that is powerful, scalable, and fundamentally compatible with life. The next time you see okra at the grocery store, do not just see a gumbo ingredient. Look at it with respect. You are looking at the future of clean water. That wraps up our deep dive for today on G Fun Facts Online. We hope this gave you a new perspective on the science sitting on your dinner plate.